Today, this lesson, derivatives of exponential functions. I won't do my line. I've been doing the last few lessons that this is the best lesson ever. But you might like components of it. You might really like what's going to happen here. Let it all develop before you judge it. Because there's two big moments in the lesson. I'll point them out when we get to them. Where you go, oh, well that's not so bad when we get there. In your notes, you'll notice I've skipped over derivatives of inverse functions. I happily added tan today, so I'm excited. So we'll get back to the inverse ones there next April. So you got to flip a couple of pages ahead to get to derivatives of exponentials. Oh, more than a couple of pages ahead. Don't worry, we'll use those pages, but not until late February, I think, is when we'll get back to that. Okay, so back to here. Derivatives of exponential functions. It's good. It's good. Wait till you see. We will begin our investigation of the derivatives of exponential functions by considering a very special exponential function. We'll focus on e to the x first. That's Euler's number. The only encounter we've had with Euler's number so far is that I graphed it and said, oh, Euler's number looks like this. And then I did a little thing where I said, using compound interest, look at it, there's a limit here to how much compound interest you can get. And there's this multiplier, 2.718. Euler's number was the most you can get out of compound interest. Sort of like an essential number to exponential growth. Like pi is an essential number to circles, it seems. Euler's number seems to be an essential number to exponential growth. You might have been skeptical when it was done. You're like, well, that was a compound interest example. You seem to pick the numbers pretty carefully to make it all work out. And I didn't really. It really is an essential number. But today's, it really brings home why Euler's number is so awesome. So we'll start with Euler's number. To find the derivative of this function, we'll use our definition of the derivative. Now, listen. It could be, after all those derivatives, that you sit at home tonight being upset by the fact that you wasted so much of your life going 2 to 2.1, 2 to 2.01, 2 to 2.001, and more of your life on msecant, and more of your life on limit as h approaches 0. You're like, why did I waste all this time? When essentially the rule is, actually let's make sure we understand the rule. The rule is, if the base is a variable, if the base is a variable and the exponent is a number, you can just bring that number down and reduce the exponent by 1. So nice. But exponentials aren't like that at all. The rule's completely changed now. The good news is the rule's even easier. Is it possible that the rule's even easier than bring the number down and reduce the exponent by 1? Yeah, this one's even easier. Watch what happens. Okay, but this situation is specifically when it's a variable up in the exponent. That's not what we've been doing. We've been doing variable as the base, some number as the exponent. And maybe the number was complicated, 2/3 or something like that, but some number, okay? So exponential. And for that reason, the rules we have don't work. You can't bring x down and reduce x by 1. It doesn't work like that. It works like this. Back to h's. You're like, oh, good, with the h's. It's really good. Watch this. It's so good. Do you remember this now? Limit as h approaches 0, f at x plus h minus f at x over h. It was like yesterday, sort of. You know, so I put in x plus h into e to the x, and I get e to the x plus h minus e to the x over h. And this is the only weird step in the whole thing is, weirdly, there's a common factor here. You may not be obvious to see the common factor, but there's an e to the x in here, and there's an e to the x in there. The weirdest common factor yet. It's not that difficult, but if I pull an e to the x out of each, that might have to go from the PowerPoint, actually. There's this old show called Fear Factor. I don't even know how old it is. That's how old I'm getting. I don't even remember how long ago since Fear Factor was on. Does anyone remember Fear Factor? It was an intense show. Like, you went on the show, and it was like a reality TV show, and all they did was try to scare you. Like, the one thing was put your hand into a box of scorpions and see how long you can keep your hand in the box of scorpions. Like, stuff like that. Just like, what? Or eat this plate of worms. And, you know, it was nuts. Not the point. The point is, e to the x factors out nicely. If you don't believe me, multiply this back in. E to the x times e to the h, I add the exponents, e to the x plus h. E to the h times negative 1, or sorry, e to the x times negative 1 is e to the x. So e to the x factors out nicely here. It's better than that. Not only does it factor out of the brackets, it factors all the way in front of the whole thing. because it doesn't have any h's in it, so I can bring it out separately. Limit laws say I can find this limit separately, sub h equals 0 into it. That doesn't do anything to it, and it's pulled out front. So my job really is to find this limit here. Now there's some really complicated ways to find that limit, a little beyond where we're at right now. So instead, I'm just going to use a table to find this limit, the old way, and just go, okay, I want h approach to 0. I'll just approach 0 by going h is 0.1, h is, I know you hate this stuff. You did a zillion of them. It still works. It's just not efficient and effective all that much. But notice where the limit heads towards. It goes 1.05, 1.005, 1.0005, 1.00005. From the other side of 0, it goes 0.95, 0.995, 0.999, 0.99999. I did it from both sides to try to convince you this limit is the number 1, our second favorite number in the universe. Only 0 is easier to work with. 1 is awesome because what I get is this limit is 1. If this is all the number 1, apparently from my table, the derivative of e to the x is e to the x. You thought it couldn't get easier than bringing the exponent down and reduce it by 1. If you look at the exponential curve with e as the base, Euler's number, and you find its derivative anywhere, the derivative will be the same value as the y value. Actually, let me draw that for a second, because it's plausible if you see it. If I go out to x equals 2 on the y equals e to the x curve, this y value will be 2 comma e to the 2. What's e to the 2? Approximately 2e squared here on my calculator. Because e is 2.718 something. So I do, where is it? E to the 2, 7.4. Apparently the y value is 7.4, but also the slope is 7.4. As the y values get bigger, the slope gets even bigger. In fact, this is the other way to come up with the curve e to the x, is to say, let's make a curve. And every time I get the slope, every time I get the y value, I'll make the y value the same as the slope. And what's going to happen to the slope as you go along there? Every y value has a slightly bigger slope, and you just keep sloping up and up like this. You're like, how do those numbers match up exactly? No, what I'm saying is, let's draw a curve where it does match up exactly. And then let's figure out what the equation of the curve is. And it's e to the x. It's perfect. It's the perfect function. I'll say that all the way through. I'll stick to my story. F at x equals e to the x is the perfect function because it's its own derivative. You take the derivative of e to the x, you get e to the x. So now, from here on in, biology, chemistry, business, you go, what base should we use? Oh, let's use 2. Oh, let's do 7. No. Stop. Let's use e as the base for this growth thing. Because any curve can be matched to this, actually. You can stretch it, compress it, do whatever you have to make sure e is your base. No problem. Blah, 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 blah. You can blah, blah, blah all the way through all that and go, hang on. So the derivative of e to the x is e to the x? Yeah, that's what I've covered so far in this lesson. Are there any other functions that are their own derivative? No, only one can do this. There's only one function that can do this. There's only one function that can have its own, the slope being the y value everywhere along the way. It can only happen once, and it's e to the x. No proof there. Let's take it for a test drive. Here, this is what you need to be able to do in the homework. All that explanation is fine, and hopefully that stuff sinks in over the next little while, but this is what you really need to be able to do. If f at x equals e to the 2x, then f prime at x, let's just rewind for a second. All I've really said so far is the derivative of e to the x is e to the x. I'm having awful time with my maths today. So the derivative of e to the 2x is e to the 2x. And before you just fall asleep and go, okay, well, that's easy. I just got to keep writing down whatever's there every single time. There is one more little thing you got to know. And by little, I mean little. It's not like some math lessons like, oh, one more little thing, and then it gets really complicated. It doesn't really get complicated here. We do have to chain rule this thing. The derivative of e to the 2x is e to the 2x times the derivative of the inside. And the inside changes where we look for the inside now. When we were doing sine, oh, there isn't one on the board, but when we were doing sine, after you were done, then you had to take the derivative of the inside of sine. The inside of e is 2x, so then I got to multiply that by the derivative of 2x, which is just 2. So let me put a comma on the sentence from earlier. The derivative of e to the x is e to the x. Then chain rule the exponent. Most times we'd write that 2 up front. It's easier to put it there. Usually in the order we put coefficients up front, then exponentials, then sine and cosine. We like sine and cosine there at the end when we have combinations of these functions. Hold on, Ms. Todd. You're saying if e is the base, the derivative is whatever it is times the derivative of the exponent. That's all I got to know. The answer is yeah. Next question. Okay, but what if e is not the base? Okay. I got one little fix if e is not the base. We'll get to that later. Let's do some with e and make sure we got Euler's number down pat, and then we'll get to the other numbers later. F at x equals e to the x squared. F prime at x. Okay, the derivative of e to the x is e to the x. So the derivative of e to the x squared is e to the x squared. Yeah, absolutely. One more little thing, though. Chain rule. And chain rule for e to the x means derivative of the inside. The inside is the exponent. That's where we find the inside of exponential. So it's e to the x squared times the derivative of the inside times the derivative of the exponent in this case, which is 2x. And it's not wrong what I've written there, but usually we bring constant coefficients, x's out front, and then do exponentials, then do sine and cosine. And there's reasons for that when we get them all combined together of keeping track of things. But that's not wrong. You just write that in the test. I'm like, yeah, that's right. I'm not even upset. I'm not even like, oh, you shouldn't have done that. It's just like, I think you're going to find from a neatness standpoint, e to the x is farther down the chain as far as what order you multiply these things in. Are there any questions? I'm going to slow the next one down and try and get some input from you guys. X e to the x. What is it about this one that forces us to bring in some other thinking from other sections? Sorry. It's product rule, yeah? Hopefully you're getting better and better at recognizing the product rule ones. When they first came up, it was like, how do I know if it's product rule? And it really comes down to recognizing that these are two separate functions. So then I go derivative of the first times the second plus derivative of the second. Derivative of e to the x is e to the x. How nice is that? Times the first. Now I also need, oops. I forgot to write the f prime there. The nice thing about e to the x too is it's almost always, because it appears in the derivative and appears in the not derivative, it's almost always a common factor. It's not hard to see, it's not hard to catch, and so you get these very nice common factors out of this, where you pull out an e to the x out of both terms, and I get 1 plus x in the brackets. Very nicely, all set up for finding zeros and so on when you want to do the next steps on these things. What questions do you have? Some people shake their head. They didn't even want to shake their head, and their head's like, yeah, this isn't bad. This isn't bad compared to, like, related rates homework is going to take you a while to get through all those circles and shapes and cars going this way and cars going that way. This stuff is like, woo, doo, doo. You can go back and forth tonight, yeah? Do a couple of related rate ones, then boo, 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 zip through a few e to the x ones. Another product rule one. If anyone's having problems with product rule, I'm going to do this underlining thing again to go, okay, there's one function, there's the other one. So, derivative of the first times the second plus derivative of the second Oh. Times the first. Explain the negative one. Where did the negative one pop out of all this? So, derivative of the inside. Okay, so these have chain rule. I was about to say chain rule every time. That's not true at all. You got to check the exponent every time and take the derivative of the exponent. Why didn't I have to do it originally? When we did e to the x, what's the derivative of x? 1. So you're multiplying by 1. When the exponent's just x, you don't have to worry about stuff like that. But always derivative of the inside. Some beautiful common factors here. I think you'll find the common factor in here much easier than in previous sections. What do I here? X cubed e to the negative x. There's almost always an e to the negative x. Or sorry, whatever the original function had for e in there, it almost always comes out as a common factor. I say almost because I just can't think of a time that it doesn't come out. Questions though? This is supposed to be the easy lesson of the day. So if it's trouble at all, you got to let me know right now. So I say the right thing so you go, oh yeah, I can handle this stuff. Is it good? More time here? E. Quotient rule now. I'll move pretty quickly. Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. Some common factoring. And then some canceling. Do you see the cancellation there? An e to the x on the top, e to the x squared on the bottom. So one of the e to the x's goes. Who's got questions? Questions? More time? Don't take my word for it that it's easy. Make sure it's easy in your head. Don't let me get away with rushing through this if it's a problem at all. Who has questions? More time? Who needs more time? No? Was there another one? Oh yeah. Crazy one. I'm going to make a mistake, okay? Now I'm going to see if you're paying attention. Mistake coming up here, okay? Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. Give you some time to stare at that and find the mistake. Derivative of the top times the bottom minus derivative of the bottom, 9x squared plus 4, yes, times the top, all over the bottom squared. Who's got the mistake? Yeah. When you take the derivative of e to the x, when I said derivative of e to the x is e to the x, you're like, oh, my problems are over. They're mostly over. Take the derivative e to the x, you got to multiply by the derivative of the exponent there. So there's a little chain rule action going on there. So there's a little 2x that has to be put in there. 3x cubed plus 4x. Oh yeah, wrong thing there. Thank you. So excited about my mistake in the numerator. Just make sure people are paying attention. I forgot to. Square the denominator. We got to talk about the denominator a little bit because it's got a bit of a problem with it that I got to deal with. But. And these ones almost always, whatever e appears, almost always comes out as a common factor. And so in the brackets I'm left with 2x bracket 3x cubed plus 4x minus 9x squared plus 4. Tried to show that all on a separate line there. And then some bracket simplification. Then I'll pause to deal with this denominator issue. That came up in the test, but I didn't punish anyone for missing it. (6x4) 8x squared, negative 9x squared, negative 4. Got one more step to do there. Now, look. I don't know why textbooks like this move. But they'll put something in the denominator that has a very obvious common factor in it. Then they expect you, in the final answer, to catch that common factor and make sure you common factor that thing out. And it can get really confusing. And there's one of the tests like that. And I put it out there to say, oh, let's just see what happens with it. And some people caught it. It was good. I really don't talk about it to this lesson. Really, in the final answer, what I should do is common factor an x out of that bracket. And have them both out separately. So I've just pulled x out of there, so I've got one more step to do. Numerator e to the x squared. Inside the bracket, 6x to the power 4. Collect some like terms there. And then the bottom is x squared times 3x squared plus 4 squared. Now you've already seen me once put that on a test, and then not get too bent out of shape when people didn't catch that little common factoring at the end. But I did want to address it. Is that just because they didn't common factor, it doesn't mean you shouldn't, even though that's seems a bit hypocritical by them, I think, to give you a question that doesn't have the common factoring, but then you're expected to handle it. Question. (2x times 4x would be 8x squared. And then there's a negative 9 and a negative 4 out of there, and then I put those two together. Is it good? Weirdly, the stuff in the bracket, somebody was asking me earlier, when do we stop with these things? You stop when there's no negative exponents, when you've done all the common factoring you can, and the factoring that's possibly left, which is right here, is so ridiculous that it would be absurd to believe it actually does factor. Only in a question that forced you to say, okay, find out when this thing's equal to 0, then you'd be like, oh, okay, I guess I got to address this nightmarish situation here and see if that thing does factor. But I want to leave that in the shelf, because next semester we're going to find out how do I get answers when they don't factor. And I'll show you some great methods of getting the answer when they don't factor. Questions there? More time? Oh, that was the last of those ones, yes? Back to the PowerPoint. Do those questions. I did them. Very good. It says, when it comes to taking the derivative of exponential functions, we've only considered one base, e to the x, one very special exponential. Leaving you go, well, that's fine. You've set it up so that, okay, that specific one is awesome. But what happens if it's 2 to the x, or 3 to the x, or 4 to the x? Because lots of the equations that are given in chemistry and biology especially, a base of e just wouldn't be convenient. Although it does pop its head up in chemistry, doesn't it? Am I right? Where Euler's number e to the x, and she probably just says to you, just press ln, and doesn't really spend much time explaining it. It does pop its head up. But sometimes we're stuck with other bases. So it's not necessarily true in general. And there's a little sad face here, even though it shouldn't be that sad. We can fix it. One little fix to the derivative when the base isn't e. Let's consider the derivative of a general a to the x function. Okay, I got to go back to my separate page here. It says, using our knowledge of the derivative of y equals e to the x, our knowledge so far is the derivative of e to the x is e to the x. And the fact that a to the x equals what? E to the x, what are you talking about? Here, let me show all the steps and then talk about what they're talking about in the middle of it. What if you got the function y equals a to the x, and it's not e anymore? So this could be a 2, or a 5, or a 10, or a 1.07 for financial math. Doesn't matter. Whatever the base is, here's my move. It's an unbelievably powerful move. It's so powerful, I need something to help me with this whole thing. Oh, I know what I'll do. Okay, I'm going to go back and I'm going to write that in black. And then I'm going to do something dramatic to show you how awesome this move is. Write this back in black. Y equals a to the x. Derivatives with the x up in the exponent. He said, really trying to help with the test question. When there's the x up in the exponent and you don't know what to do, here it's called logarithmic differentiation. It's so good. I'm gonna teach more of it. You're gonna see more of it before in the homework and so on. But here's the move. Take log of both sides, not just log, ln of both sides. You're unconvinced. You're like, why? Why are you doing this? You're just making up stuff. Yeah, maybe. Watch what happens to this thing. I'm going to highlight that in red, like in blood. Like, look at this. This is the greatest move for specific functions where there's the variables up in the exponent. And how do you know that's such a good move when the variable's up in the exponent? Because log laws tell you that when there's a variable up in the exponent, you can just bring it down as long as it's a log. So first move, make it into a log. Second move, bring it down. Now instead of it being an exponent, it's a multiplier. And watch this move, which just looks like cheating, except it's so awesome. Okay, we got to rewind here to make sure it's clear. We did a bit of this, but maybe not enough. The opposite of adding is subtracting. You want to move it over? You want to move adding over? You got to do subtracting. The opposite of subtracting is adding. The opposite of multiplying is dividing. Dividing is multiplying. Squared, square root, square root, square root. Everything's got an inverse. And the inverse of ln is e to the power of whatever's there. That's the inverse. And if that's confusing, don't forget, we talked about this before, is check out this one. X squared equals, 9's no good, 11. Back when you were first learning about squared, somewhere along the way, a teacher said, if x squared equals 11, let's see, 3 squared is 9. Okay, it's not 3. 4 squared is 16. Oh, it's not 16. Oh, no. And you didn't know how to invert x squared. So you had to learn about it. And the teacher said, okay, what we do is we write this square root of 11. And to you, it's like obvious. You're like, yeah, x squared, square root. And imagine if you're explaining this to your little cousin, you're like, I don't know. That's just what you do. Stop asking me questions. Like, squared, you write the little checky do, square root. They're inverses of each other. You've learned that. Here, that's what's happening here. Ln, e to the. That's what the inverse is. Ln and e to the are inverse of each other. That's what they were saying here. A to the x, here, look here. A to the x is e to the x ln a. And it's not less complicated. It's way more complicated the way I've written it there, but it's now ready to take the derivative. Because it's e to the. I know how to take the derivative of e to the x. Y prime is e to the x ln a. Times the derivative of the inside. And the derivative of the inside, it's x times ln a. It's just ln a. Whatever a is, whatever the base is. Listen, this proof is a little bit difficult. If by the end you're like, I'm about 40% on this whole thing, wait till you see me do the examples. Because when I do the examples, you'll be like, oh, not too bad. It's not done that, though. I'm going to replace e to the x ln a with the original a to the x. That proof is not on the test. It's a good proof to know. I'm going to do more of those in second semester with arc sine and arc cos and all those ones we skipped over. The lesson we just skipped over. I'm going to do them like about 10 in a row to the point where these kind of proofs are like, oh yeah, yeah, yeah. So for now, if you followed along with them, I sort of got most of the steps, and this is just an intro to these types of proofs. I like it. Our end result, though, is when the base is not e, the derivative, so we've got a to the x, the derivative of a to the x, it's a to the x. You can sort of remember this next part as your correction factor. It's like your punishment for not using e as the base, right? So math people show up. The chemists have some kind of curve. And they're like, oh, it was exponential growth. The math people go, okay, let's use e to the x then. Chem people are, no. Because of the nature of what's going on, we want to talk about doubling time. We're going to use 2 to the x as our base, and you can have stretches and compressions and all this stuff to match the base. Yeah, that's fine. And the math people go, okay, well, your punishment for not using e to the x is that when you take the derivatives, you've got to multiply by ln a to get the right answers. It's not the worst punishment ever. And let me get right to examples to show you how it works. Oh, here we go. Do this from current slide. Okay, here we go. There it is in a box. If f at x equals a to the x, instead of e as your base, if you want to take the derivative, yes, you just make a to the x, but then you've got to multiply by ln a. So here's the example. Instead of e to the x, let's say it's 5 to the x. 5 is the growth factor we're talking about here. The derivative is 5 to the x. Just like e to the x, derivative is 5 to the x. Except you've got this correction factor of ln of whatever the base is. I did prove it, but again, you're not responsible for the proof yet. It's more of an intro to those kind of proofs. Derivative of e to the x is e to the x times the derivative of the exponent. Derivative of 5 to the x is 5 to the x, but because you used 5, you got to pay this penalty of having a correction factor of ln 5. And then this one. Derivative of 5 to the 2x minus 3 is 5 to the 2x minus 3 times your correction factor, ln 5, ln of the base, times the derivative of the exponent. Couple of skeptical looks there. I get it. Things seem to be complicating up here. I'm telling you it's not. Related rates, the lesson from earlier today, yeah, there's some complicated stuff in there. That homework's going to send you for a loop. This will not. By the time you do a few of them, you're like, oh, okay, I got it. This times this times this. You just got to practice a few of them. This is just writing in a different order. We like to write the coefficients out front. So that's just a choice. That's totally fine, the way it is on the first line there. Questions you have about those two? Last example. Here we go. At what point on the graph of the function y equals 2 to the t minus 3 does the tangent line have slope 21? So y equals 2 to the t minus 3. And I'm going to make a mistake here. And hopefully someone will catch it. I want slope of 21. Okay, so I need y prime. The derivative of 2 to the t is 2 to the t. Right? The derivative of e to the x is e to the x. The derivative of 2 to the x is 2 to the x. Something missing. What's the missing piece? Derivative of the inside, in this case, yes, we should consider that. Well, the derivative of the inside here is just 1. So you could write it, and I see it all the time once we've done chain rule. There's people writing these 1s everywhere, and it's not wrong. It's just we could neglect that. But when the base isn't e, what do we need here? Ln 2. So if you want, that whole lesson is derivative of e to the x is e to the x if the base is e. The derivative of things that aren't e as the base, you got to multiply by ln of the base. That's it. But in this case, we want slope 21. So I need 21 equals 2 to the t ln 2. Ooh, a little review of solving exponential equations here. I got to dig that 2 out of there. One step at a time. Don't tune out just yet. I'm almost done for the day. This last example. Stay with me. Solving for things that are up in the exponent. A little bit of isolation first. I'm going to bring the ln 2 over. And there's several ways to handle this. But the most powerful way to handle it when you've got something up in the exponent is take lns of both sides, or whatever log you want, allowing you to bring that down. And then you can finish isolating. Okay, you should have questions there. That's reaching way back into, well, Unit 1, we did a little bit of it in the exponential function section. And we did a little bit of it online during COVID shutdown. But that is a tough finish there. Which step would you like to talk about? Maria, thank you. Oh, yeah, she says, can't you just use logs? And the answer is yes. The convenience of ln and e is like, given your choice, just like here. If this curve came up, the mathematicians would immediately go, let's use e as the base. And we'll stretch and compress it from there to make sure this matches e. And the physicists and the biologists and the chemists might go, we really want base 2 for this reason, that reason. Okay? When we're doing math, we like ln because its derivative, when we get to it, is much simpler than other bases. So whenever we get a chance, we use ln. It works together good with Euler's number. So there's good reasons to use ln all the time. However, any log will work, including log base 2. The way I taught this in here, 21 equals 2 to the t, 21 over ln 2 equals 2 to the t. The way I taught this in advanced functions, at that point, our favorite log was log, just log base 10, because it was on everybody's calculator. So we would have just log both sides, and you would end it up with and your final move would have been that. If you type these two things in your calculator, you get the same answer, which is mind-blowing, but it has to be. It has to be that they both work. Log base 2 will also work here for those of you who have a calculator with log base 2 on it. You might have just gone log base 2 of 21 over ln 2. Totally works as well. So you've got many choices there. I'll lean on ln because I know there's sometimes when ln is the most convenient ones, and so I'm leading up to that. But you can deal with that when you get to it too if you're totally used to using logs instead. Here, if I had then switched it over e to the power of, it would have taken this ln and would have canceled out, and I would have been right back to here again. The whole idea of using logs is to then bring this exponent down up front. That's the whole reason that we use logs, is we want to get that variable that's up in the exponent down so we can use it. We've got lots of rules for dealing with multiplying and so on and dividing, but logs allows us to use those rules by getting that exponent out of, the variable out of the exponent. Other questions? How did I do on the question? Are we okay? Yeah? Other questions? Don't underestimate this stuff, especially you people that are thinking bio, chem, medical. Yeah? Because what happens in first year calc is it depends on what you're going into, what they focus on. I didn't get much experience with this stuff in my first year calculus course because I was heading off to physics, computers, that pathway, and they're like, well, we need lawn, but we don't, we don't do a lot with exponential growth in these kind of pathways. This is not a normal physics thing. It does come up in physics, but it's not a normal physics thing. Sine and cos is everything, wave functions, everything. So everything was derivatives of sine and cos. Go off to biology and chemistry. I'm only learning this 10 years later after I started being a teacher. They're way more into this because exponential growth, this is biochem, leaning. So I've tried to modify the lessons to cover both sides of it.